Hello, welcome to my channel. Today we are going to discuss about how to display poles and zeros in MATLAB when a transfer function is given to us. For example, this. The transfer function represents the system's response to input signal in the discrete time domain. In transfer function, we have to find the poles and zeros, which will eventually give information about the system's behavior and the stability. The transfer function will most likely have a numerator polynomial and a denominator polynomial. From the denominator polynomial, if we find the roots, we will get poles. Poles are those for which the transfer function will become infinite. And if we find the roots of the numerator, we will find zeros. Zeros are in for which the transfer function becomes 0. So let's dive into the MATLAB code. Initially, we will have clear all, close all, and CLC, which is the standard code. It doesn't matter if you write it or not, but it makes things easier. Then we create numerator array variable to store numerator coefficient and a denominator array variable to store denominator coefficients. These coefficients are the polynomial coefficients. For example, like that. We pass the two variable into the built-in MATLAB function zplane as numerator comma denominator. Then we hit run. A graph will be shown, a figure will be shown with circle as zeros and x as poles on the graph. And if you go to the top option and select data cursor, you will be able to know the coordinates of the zeros and poles. After finding the zeros and poles, we can use this to determine the ROC of the transfer function, which will eventually give the stability of the system. Since we found the pole, we can now specify ROC and determine if the system is stable or not under three conditions. If the system is causal system, we take the outermost pole, then we shade it outwards. If the unit circle falls in the shade, then the system is stable. If not, if it does not fall in the shade, it is unstable. For example, on the diagram given, this if it is a if this is a causal system, the system will be stable. Then we move on to anti-causal. If the system is anti-causal, we take the innermost pole and shade it inwards. Again, if the unit circle does not fall in the shaded area, it's unstable. Then we move on to non-causal system. In non-causal, we take the outermost pole and the innermost pole and we shade it in between. It forms a ring. If the unit circle falls in the ring, then it is stable. If not, unstable. And when I mean the system is stable, it means the response graph will be a bounded graph. It means it will decay, exponentially decay. It will be a finite graph. For unstable graph, it will exponentially rise. That means it is going to be infinite. And if it does not decay or rise, it means it is neither stable nor unstable. And we will see the example later on. For the transfer function given to us, if we consider it to be a causal system, we can study the time domain behavior of the signal. In this video, we will just look at the effect of only single pole, which means we have on the screen, we have just only single pole. There will be multiple poles as well, but in this video, we will just look at the effect of single poles. And for that, we will use another built-in function called IMPZ. This function will generate and plot the impulse response of our system. Basically, we give an impulse input and see the system's response over time. This will give idea about the stability. You can directly find information about stability by seeing the ROC and guessing where the unit circle falls on the shade. But if you want a clear graph as impulse graph, you can use the IMPZ function. And the impulse graph will be either exponentially rise, decay, or just be a straight constant line. So if we write the impulse response code, it is the same as the z plane. We give numerator comma denominator, and that's it. And we hit run. By looking at the pole's location, we can easily identify that it's at 0.9. And since it's a causal system, as I said before, we will take now 0.9 and shade it outwards. Shaded outwards. Does unit circle fall under the shade? Yes. That means it's a stable, and stable, as I said, stable, bounded, and finite graph. If we now look at the impulse response graph, we can see that it is decaying. That finite, that means it is stable. The impulse response is showing stable. If for reference, you can look at the given chart. Now if we change the pole location from 0.9 to 1, as from the graph, we can, if we put 1 and hit run, we can see that it neither decays nor it rises. It's just a constant. That means it is neither stable nor unstable. It's just a constant graph. If I give you a small information, we are talking about basically the positive poles. For the negative poles, you will get the same impulse graph. If the code will be the same, just look at the reference chart I gave you. It will be the same as this. Now if we change the pole location from 1 to 2, let's see what happens. If we hit run and check the impulse response graph, it is exponentially rising. That means unstable and an unbounded graph. Why is that so? Because if we take, since it's a causal system, we take the outermost pole, then we shade it outwards. If we take 2 and shade it outward, does the unit circle fall in the shaded region? No. That means it is unstable, and we can see from the impulse graph that it is not getting bounded, it is not decaying, it is just rising up. So the impulse response graph proves that it is not a stable system. To see the effect of the negative pole, we just change from minus 0.9 to positive 0.9, and the pole position will be at minus 0.9 on the graph. If we hit run, we can see that the impulse response graph is a decay envelope reaching towards 0, which means it is a bounded graph, and bounded and finite graph, that means it is stable. It's the same as the positive pole. Then if we change the pole value to 1, we get the same constant value, constant graph, not stable, not unstable. The impulse response graph, you can see that. And if we now change the pole value to just 2, that means on the pole position it will be minus 2. The impulse response graph is a slowly exponentially rising graph, exponentially rising envelope curve going away from 0. That means it is a infinite unbounded graph, which means it is unstable. Such graphs are unstable. It is the same as the positive pole, where we are getting an unbounded graph as well. Now if we check our reference table, you can see that we got the same graph for almost all the pole positions, both for the positive poles and the negative poles. That is it for today's video. I have covered both z-plane function and the IMP impulse function in MATLAB. That's it for today. Thank you.